Hello friends, I am Dr. Anil Parmar, Assistant Professor at Department of Mathematics, R. Mehta College of Science and C.L. Parikh College of Commerce, Palanpur.
Hello friends, today we are going to learn Unit 2 of our differential calculus, that is CC Mat 301. Name of the Unit 2 is Applications of Partial Derivatives. First of all, we have to learn about the especially homogeneous function. So now, without wasting much more time, what is homogeneous function? So homogeneous function is basically a function f from E, which is subset of Rn to R, is said to be a homogeneous function of degree m in if f of ix is equal to I raised to m f of x, that is known as the homogeneous function of degree m. So let us consider the example for our better understanding. That is, if x plus y is non-zero, f of xy is equal to x raised to 4 plus y raised to 4 divided by x plus y. So first of all, here we consider f of tx and ty, so is equal to x replaced by tx and y replaced by ty in the function f of xy. So we get t raised to 4 x raised to 4 plus t raised to 4 y raised to 4 upon tx plus ty. So we take a common t raised to 4 and we have x raised to 4 plus y raised to 4, x raised to 4 plus y raised to 4 divided by t x plus y. So here we have a remaining part f, sorry, so we get f of t x ty is equal to t cube x raised to 4 plus y raised to 4 divided by x plus y. So is equal to t cube f of x comma y. Therefore, f is homogeneous function of degree 3. So in this way we can show that f is homogeneous function of degree 3. Now the very most important theorem is Euler theorem on homogeneous function. Homogeneous function. So in this examination they may ask state and prove Euler theorem for homogeneous function. So for that we state the theorem is like f is if f is a differential homogeneous function of degree m with variables xi for all I vary from 1 to up to so on, defined on the non-empty set E, which is a subset of Rn, if and only if summation I vary from 1 to n xi del f upon del xi is equal to m times f of x. So here strictly we note that the f is the function of degree m. So m come outside of the function and it is m of f of x, m into f of x. So now we moved on the proof. First of all, assume that f is differentiable homogeneous function of degree m with variable xi, where I vary from 1 to n. So for that we consider the function f of x1 x2 up to xn, and we give name of this function is u. So we take x1 common from u and we have u is equal to x1 raised to n f of x2 upon x1, x3 upon x1 up to xn upon x1. Now suppose xi upon x1 is equal to vi, where I is what? I is 2, 3 up to so on. Therefore, u is equal to x1 raised to n capital F of x2 upon x1, that is v1, sorry, v2, v3 up to vn. So now we apply the derivation from both sides of the function u with respect to x. So it is del u by del x1 is equal to, first of all we have a derivation of x1 raised to m, that is m x1 raised to m minus 1 into f as it is plus x1 raised to m as it is, and the derivative of f with respect to v1 and v derivative of v1 with respect to x1 plus derivative of, so it can be written as like this, now is equal to m x1 raised to m minus 1 f plus x1 raised to n summation I vary from 1 to n del f upon del vi, and del vi upon del x1 is, where vi is xi upon x1, so it is minus xi upon x1 square. So we can write is m x1 raised to m minus 1 f minus x1 raised to m minus 2, as in the last f in denominator we have x1 square. Summation I vary from 1 to n, sorry, 2 to n. I vary from 2 to n xi del f upon del vi. So it will become like x1 raised to n del f upon del vi into del vi upon del xi. But it is what? It is nothing but the del u by del xi. So it can be written as del u del xi is equal to x1 raised to n del f upon del vi into 1 upon x1, as vi is equal to xi upon x1. So it will become x1 raised to m minus 1 del f upon del vi. Now it is our equation number 2. It is our equation number 2. So multiply the equation number 1, that is shown here. Multiply the equation number 1, that is shown here. So x1, now multiply the equation number 1 by x1 and equation number 2 by xi, and adding them, and we get the summation I vary from 1 to n xi del capital F or del u by del xi is equal to x1 del u by del x1 plus summation I vary from 2 to n xi del u by del xi. So it will become mx1 raised to n capital F minus x1 raised to m minus 1 summation I vary from 2 to n xi del f by del vi plus x1 raised to m minus 1 summation I vary from 2 to n xi del f upon del vi. But here this term and this term are equal, so we get only the we get only the summation I vary from 1 to n xi del f upon del xi is equal to m x1 raised to m f. So it is nothing but m f of x1 raised to m is come to the inside of capital F and we get small f x1 x1 x2 up to so on xn, and so we can say that Hence, we can say that summation I vary from 1 to n xi del f upon del xi is equal to mf of x. So now, in the converse part of assume that summation I vary from 1 to n xi del f upon del xi is equal to m into f of x, and we have to prove f is differentiable homogeneous function of degree of degree m. So please wait a while. So for that, for that let v is equal to f of tx1 tx2 up to txn for t greater than 0. Put txi is equal to capital Xi where I vary from 1 to n, and we get v is equal to f of capital X1 capital X2 up to capital Xn, and we say that d capital Xi upon dt is equal to small xi. Therefore, dv by dt is equal to summation I vary from 1 to n del f by del xi and del xi upon del t. It is nothing but summation I vary from 1 to n del f upon del capital Xi into small xi, as dxi upon dt is equal to small xi. So we multiply t to the both side and we get dv by dt is equal to summation I vary from 1 to n t xi del f upon del xi is equal to summation I vary from 1 to n txi is capital Xi and it is del f upon del xi. So, but we have xi del fxi, but we have summation I vary from 1 to n xi del f of xi is equal to nf is equal to summation I vary from 1 to n xi del f upon del xi is equal to nf by Now, now as we have what we have summation I vary from 1 to n xi del f upon del xi is equal to mf, where m is the degree of homogeneous function. So we apply this result in the last statement formula, and we get summation I vary from 1 to n capital Xi del f upon del xi is equal to n f of x1 x2 up to xn is nothing but mv by the result, and it is our equation number 4. Now by equation 4, t dv by dt is equal to mv. So by the rule of separation, we have dv upon v equal to m dt upon t, and we solve this differential equation by integrating both sides. Dv upon v is equal to m integration dt upon t. So we get log v is equal to m log t plus constant, that is log c, and we solve this and we get v is equal to c t raised to n. Now if t is equal to 1, then c is equal to u. Therefore f of tx1 tx2 up to txn is equal to t raised to n f of x1 up to xn. Therefore f is a homogeneous function of degree m. That's it. Here we completely prove this theorem. Now in the next lecture we are going to learn about the corollaries of this function. Thank you.